Thanks for the introduction, Tom, and thank you all for coming. As Tom said, I'm going to be talking about the NASA AIM mission, which is the Aeronomy of Ice in the Mesosphere. LASP built 2 instruments that are on the AIM satellite, and we also do the mission operations, and some real heroic efforts actually have gone into the mission ops that have allowed us to keep operating 6 years actually after we were launched. So, as Tom said, we are looking to study clouds in the Mesosphere. These clouds, by some names, are called Noctilucent or night shining clouds, also known as NLCs. This is a picture here of the Noctilucent clouds, and as you can imagine from the name, they are seen at nighttime from the Earth's surface. So you can see this picture was taken at night, and then the clouds appear to be pretty much like glowing in the nighttime sky. This was over Scandinavia. NLCs are also known as polar mesospheric clouds, and that's how I will be referring to them throughout this talk. So polar mesospheric, so they are in the polar regions in the mesosphere. So this gives you a plot of the temperature of the atmosphere versus altitude. You can see in the troposphere, the temperature, of course, it gets colder as we go up in altitude. In the stratosphere, it gets warmer because ozone absorbs ultraviolet light and heats the atmosphere. Then in the mesosphere, the temperature drops again, and the polar mesospheric clouds form at the very coldest place in the mesosphere, near the mesopause, the top of the mesosphere. And they form at these areas where you have cold temperatures because it needs to be cold, of course, in order for water vapor to condense. So that mesopause region is about 50 miles up above the surface of the Earth at what we often refer to as the edge of space because the atmosphere is getting so thin up there. And just to put these clouds into context, these are pictures of other clouds that you are certainly familiar with, some maybe not with others, but cumulus clouds about a mile above the surface of the Earth or so, cirrus about 6 miles, and then there are the polar stratospheric clouds. So these are in the stratosphere about 12 miles above the surface of the Earth. These are very important for ozone processing and in fact are responsible for the ozone hole. And then there are the polar mesospheric clouds that are way up here 50 miles above the surface. Okay, so PMCs, we said, form in the polar mesosphere. What's important to understand about these is that they form in the summer polar mesosphere. And what's interesting is that you can see these are temperature profiles in the atmosphere, starting in the upper stratosphere, going through the mesosphere. The summertime temperature profile shows that the temperature is much colder in the summer than in the winter. So that might be a little bit of a surprise because normally we think, well, if the sun's out in the summertime, it's going to be warm and it should be warmer than it is actually in the winter. The explanation for this, though, is that circulation is causing the temperatures to actually be colder than you might otherwise expect. So we're actually going to look at this figure a few times tonight, but just to explain it very briefly, what this shows is the meridional circulation and the winds, and how the transport of material, the air will ascend in the summertime latitudes in the mesosphere. These are from 60 to 80 kilometers. It's then transported from the summer to the winter hemisphere, and then it descends at the winter pole. Right? So you have ascending air in the summertime polar region. When air ascends, it expands, it cools. That's what gives you the very cold temperatures at the summer polar mesopause region. So this just shows that same concept a slightly different way. So you have air that's ascending, maybe it's starting out cold, it's getting even colder, expanding. When it finally gets to the near the mesopause, the expansion has cooled the air, so the H2O water vapor condenses, forming the PMCs. It turns out that you can't just go outside in the middle of the day and see these clouds, even if you were at the near the polar regions where they would appear. They're very tenuous. They're very thin clouds, and they're too dim to be seen during the day because there's a lot of Rayleigh scattering, or just scattering of sunlight by air molecules in the sky closer to where we are. However, because they occur so high in the sky, if you are in darkness, the sun might still be lighting up the air in the mesosphere. So if you're a ground-based observer standing on Earth, the clouds in the troposphere, which we're we normally would see are going to be dark, so you're not really going to see those. But the sun is going to shine on these clouds that are high in the sky, the polar mesospheric clouds, and they can then scatter light to your eye and you can see them. So if you look about an hour or so after sunset, an hour or so before sunrise, for a period of about an hour and a half or so, you can see the polar mesospheric clouds if you're at the right latitudes. I should say that even though on the ground you can only see them during the night, if you're on a satellite, you can actually see them both in the night and in the day. It turns out that the instrument that we're looking at actually, for technical reasons, can only see during the daytime, but there are other instruments that could see at night. Okay, you might be asking, why in the world would we want to study these clouds? Well, they have been increasing with time. This shows a plot of cloud brightness at different latitudes between 50 and 64 degrees north, 64 and 74, and 74 and 82. These are measurements of polar mesospheric clouds from the solar backscatter ultraviolet series of instruments. They were able to detect the clouds, measure their brightness, and you can see that the clouds have been increasing in brightness. At the same time, they've also been appearing at lower latitudes. This is a photograph here that was taken from Utah at almost 42 degrees latitude. And you can see here, tropospheric clouds are very dark, right? That's because it's been taken at nighttime with a long enough exposure that you can actually see some structure in it. But the polar mesospheric clouds here are lit. So you can see them very clearly. They have really wonderful structure that we'll be talking about a little bit later. The clouds have even been seen over Boulder. I've never seen them myself, actually, but there have been reports and photographs over Boulder. Okay, so they've been becoming brighter. They're showing up at lower latitudes than we thought they ever would have occurred. The question is why? And one of the things we're wondering is whether or not our changing climate plays a role in this. And there are two reasons that you might expect the climate to play a role. One is, we know that we have been releasing more CO2 into the air. This plot shows the CO2 in the red line going from, for the past 2,000 years. You can see that we have huge increases recently. Well, CO2, we mostly know it as something that causes global warming, and that's because at the surface in the troposphere, it does warm the atmosphere. But in fact, it's a very efficient radiator, and while that radiation might not actually escape the troposphere, when it's up in the mesosphere, that radiation does escape to space. So if you put more CO2 up there, you get more radiative cooling, and the mesosphere can become colder. If it becomes colder, then you have a higher probability of clouds. And so that's one reason. The other thing is we know that we are releasing more and more methane due to things like agricultural activity and energy use. And you can see here the methane in the green has also been increasing dramatically as a function of time. Turns out methane is the source of water vapor in the mesosphere. So if you release more methane, you're also going to have more water in the mesosphere and therefore a higher probability of clouds. So both of those reasons might play a role in what we've been seeing with the clouds changing. So AIM was launched in order to figure out really what are the natural causes of variability in the clouds, and can we ascribe some of the changes that we're seeing to climate change that in fact people are causing. So we were launched in 2007, studied how they form, why they change. We were launched on a Pegasus rocket, which is here. It's on the underbelly of this plane here. What happens is the plane will take off, and when it reaches altitude, it'll drop the rocket, which will ignite and then be launched into space. This is just an artist's rendering of what it might have looked like in space. The satellite is up in the front there. And then this is what it might look like actually in space. Here you can see its solar panels are extended. It has 3 instruments on it. This is the cosmic dust experiment. Sophie SIP's down here and Sophie there, and I will talk about those in just a second. Okay, so these are the instruments. So this is Sophie. It's called the Solar Occultation for Ice experiment. It's an instrument that measures the concentrations of different constituents in the atmosphere and also the temperature. It measures these as a function of altitude. So you'll get what's called a vertical profile of different constituents, and some of the ones that are important for understanding polar mesospheric clouds are, for instance, it will measure water vapor. It will measure water ice, which is what the clouds are made of. It also measures meteoric smoke, and we're going to talk about that in a second. and it measures temperature, along with a few other constituents. Okay, this is the CIPS instrument, Cloud Imaging Particle Size Instrument. This is one of the instruments that was built here at LASP. It's actually a set of 4 cameras that you can see here. This actually is a big sunshade on one of the cameras. And in fact, these, just got tonight, these are the actual camera mounts. Well, not the actual ones, obviously, they're just models, but I wanted to come up and look at them afterwards. What CIPS does is, again, it has 4 cameras, so CIPS looks down on the Earth and takes pictures of the clouds. Now we look at the clouds using light that's at a wavelength of 265 nanometers. So in the ultraviolet, you can't see it yourself with your eye. The pictures that we get look pretty much like black and white images that you would expect from a camera. But we use that wavelength because the clouds will scatter that into the camera, and their signal will not be interfered with by light that's shining from below the clouds, because the Earth is very bright in other wavelengths. And then finally, the Cosmic Dust Experiment, CDE. This detects dust particles, meteoric smoke, coming into the atmosphere. Unfortunately, it only lasted a season. I'm not going to be talking about its results here. We believe it was, after one season, it was hit by energetic particles, electrons and protons from the sun or magnetosphere, and that caused it to be too noisy to be able to interpret the data. Okay, so I'm going to be talking the rest of the time then about the science highlights from the AIM mission. Not all of them, but I'm just going to highlight a few different areas. So first of all is SOFI can measure meteoric smoke, as I mentioned earlier. And in fact, this was the first time that a satellite had been able to measure meteoric smoke. So they can actually get the profile and see where the meteoric smoke maximizes. It turns out when meteors come into the atmosphere, they deposit their energy, they break up right around the mesopause region. And meteoric smoke is important because clouds in the mesosphere, just like in the troposphere, need some sort of a condensation nucleus for the water vapor to condense onto. So they need some sort of a seed. And when AIM was launched, we didn't really know what that seed was. It certainly had been hypothesized that it was meteoric dust, and that's why we built the Cosmic Dust Experiment to measure that. But there were several other hypotheses as well. But not only were we able to measure the meteoric smoke, but we also, with the SOFI instrument, were able to measure the PMC particles themselves, and because they have some spectral information, they were able to deduce some of the composition of the clouds, and they were able to conclude that the PMC particles do contain meteoric smoke, which pretty much suggests to us that, yes, the meteoric smoke is the condensation nucleus used to form the clouds in the first place. Okay, another thing that SOFI showed, which was quite a surprise, was that ice is so ubiquitous in the summer. SOFI is a very, very sensitive instrument, probably the most sensitive instrument that is currently making observations in the mesosphere right now, and that has ever made observations in the mesosphere. And what this shows is a plot of the brightness of the ice, basically the amount of ice in the mesosphere, so ice being what's forming the clouds, so you can think of this as the number of PMCs, as a function of time during one season. So we're talking about days from solstice, the summer solstice being around June 21st in the northern hemisphere. And this is from 20 days before to 60 days after or so. You can see that ice exists from about 80 kilometers up to 90 kilometers. That maybe doesn't seem so much, but it's 10 kilometers, and previous to this, we thought that it was mostly concentrated just right here, about 83 to 84 kilometers or so. And I think what was also surprising was that it exists for such a long time during the season. It's not like it starts out just at 83 or 84 kilometers and then gets broad and then goes skinny again. For most of this time, it actually exists throughout this altitude range.
Is the black dashed line in the below?
Sorry, yes, the black dashed line is the mesopause, the coolest. So you can see the clouds mostly form just below the mesopause. Okay, so now I'm going to talk a little bit about some of the CIPS measurements. If you were here beforehand, you saw the movie of what we call CIPS daily daisies. So these are polar mesospheric clouds here as measured by CIPS. So this is that black and white image which we have colored to be blue and white to look a little bit more like clouds. we call it the Daily Daisy because you can see that this has spoke-like things, a little pinwheel almost, but basically every single orbit, I'll show you what an orbit looks like, but it makes it look like you have petals on a daisy. This is 1 day's worth of observations. Our resolution is 25 kilometers squared, so it's about 3 miles by 3 miles. That seems very big if you're thinking about the troposphere, but in fact, it's better than any other satellite instrument can look at these clouds. So it's very high resolution as far as satellite instruments go, and so we're learning a lot more about the structure in the clouds. So this shows an actual orbit strip. So every time, AIM goes over the pole, so it orbits over the pole, looks down, and it does that 15 times a day. So we get 15 orbits where we're imaging the clouds over the polar region. One orbit looks like this. We put them all together into this daisy, and this is how the orbit would be superimposed on the daisy. You can imagine that these orbits all overlap at the high latitudes. So what you see here is kind of a qualitative picture because one orbit is going to hide another one. So when we do quantitative work, we usually are looking at these orbit strips themselves. And I'll show you some more examples of those later.
But some of the overlay you've added them all together, or?
So yeah, what happens here is we take all of them, position them correctly on the Earth, and then we actually take the brightest spot, because the idea for these daily daisies often is to show people where the clouds actually appear. And so we want them to know if there's truly is a cloud there, that that's what it is. We could take the average, we do brightest. Okay, so here's one of the new findings that we had, is that, well, when space exhaust from, say, a space shuttle is emitted, it'll actually cause PMCs to increase. We actually had an idea of this, but we were able to see it better than we had ever seen before with the SIPS images in conjunction with some other measurements, other satellite measurements. So the very last shuttle mission was launched on 8th of July, 2011. This was SDS-135. 8th of July, what this shows is a map of the Earth over Scandinavia. You can see in the gray region, this is Scandinavia. The white region is ocean. This gray stippled region is where the SIPS orbit actually went. No clouds on that day. But on the 9th, you see lots and lots of very bright clouds right in that region. And then they were gone by the next day, or mostly gone. That in itself would not have told you that the space exhaust actually did anything. But what happens is, when the shuttle launches, it releases a plume of exhaust, and that plume contains a lot of water. In fact, 350 tons of water each time the space shuttle launches. Other instruments were able to track that plume and watch it move up to the north. So it was launched, the plume was basically off the east coast of the United States, somewhere near Florida, and then it was transported up to the polar region. And we were, with other instruments, we were able to watch the transport of that exhaust until it reached this region, where it then formed the PMCs very quickly. So just the extra water is what led to that. Okay, here's another study, very different sort of study. Christian von Savigny, who's from Germany, was interested in the structure in the clouds and just wondered, are they fractal in nature? So something that's fractal in nature basically has the same type of pattern at smaller and smaller and smaller scales. It's just a repeating pattern. And mathematically, you can define that as the area being proportional to the perimeter raised to some power 2 over the fractal dimension. So you can actually calculate the fractal dimension of something if you compare the area to the perimeter of some shape that you're looking at. And for instance, the fractal dimension of a circle, rectangular, square is 1 because it's because the area is proportional to the square of the radius. The fractal dimension for irregular shapes is going to be greater than 1. Okay, so what Christian did is he took clouds from AIM, which is what these are. So this blue area is all a contiguous cloud from one particular SIPS image, or SIPS orbit. This is another cloud, this is another cloud, et cetera, et cetera. They are not connected by anything. Each one of these little teeny squares is a SIPS pixel. So what he did is he said, okay, well, I'm going to measure the perimeter, And then I'm going to measure the area in terms of numbers of pixels in the SIPS camera, and I'm going to compare the two. And what he found is that when he did this, no matter if he did it with this shape or these little shapes, he got pretty consistently a fractal dimension of about 1.3. If you look at tropospheric clouds, you can do the same thing and you get a dimension of about 1.35. Those are pretty close to one another. So what he concluded from this is, first of all, the polar mesospheric clouds are probably a little bit like tropospheric clouds. The fractal dimension, in ways that I can't go into, is related to the processes that actually cause the clouds to have the formation that they do. And so if you have the same fractal dimension, you might infer anyway that you have similar processes. We don't know that for a fact yet, but that's one of the assumptions that that's one of the inferences that we're making at this point. We need to look further to see in more detail if that's the case. The other thing is just that they are fractal in nature, which was an interesting finding. Nobody had ever seen that before. And that allows us then to have an extra diagnostic for our models. So you can, when you use a model and try to simulate a polar mesospheric cloud, now you can say, oh, well, what did the model tell me about the fractal dimension was, and is that similar to what AIM saw? Okay, so we see lots and lots of different kinds of structures in the clouds. I'm just pointing out a couple different ones here. This is from a paper written by Brenta Thuraja, who is currently at Virginia Tech. She noticed that we have these structures that look like rings in many of the clouds. So this is a few different orbit strips from 2007 in the Northern Hemisphere. You can see a ring here, you can see partial rings here, looks a little bit like a 3, and then you can see concentric rings here. These, we believe, are evidence of turbulence in the mesosphere. It's unclear exactly what forms them. One hypothesis that people are looking at is that you have convection in the mesosphere. So convection, that you're familiar with it, would cause thunderstorms and things. You have air that's uplifted, so it cools, so you're going to get clouds to form, but then to balance that out, you also have a downdraft, and that's going to cause the air to compress and warm. So you might get areas where you actually have this convection forming these bright rings, and then inside or on the outside of that, you have much dimmer clouds, or none at all. These concentric rings are actually a slightly different effect, and I'm going to talk about them in a couple slides. But in order to understand those, you have to be introduced a little bit to the concept of gravity waves. These are atmospheric gravity waves, not to be confused with gravitational waves in the universe. Okay, so these are all in our atmosphere. They're called gravity waves because their restoring force is buoyancy, which is just a balancing gravity. Okay, so the gravity waves can be generated by things like turbulence in the atmosphere or flow over mountains. This gives you an example of what happens if you have flow over a mountain. So you have air come, hits the mountain. Well, it doesn't really hit it. It sees the mountain and it goes up, right? Well, as it goes up above the mountain, it's going to expand and cool, right? So as it gets to the top of the mountain, you're going to get condensation. You're going to form clouds. In fact, this is why you see our mountains are often capped with clouds. It then heads back down the mountain. It compresses and warms as it compresses, and therefore you're not going to form the clouds there anymore. So basically, it descends, compresses, warms, but it tends to overshoot when this happens, and it forms a wave pattern then. Just like on a spring, if you pull a spring and then it'll kind of bounces until it finds its equilibrium position. That's what happens in the atmosphere. So it forms this wave-like pattern where it's bouncing around, going down, and then ascending, expanding. You can form the clouds as it cools, and then like that. So you get this row of clouds like this. The same thing happens in the mesosphere. You can get, when you have gravity waves, you'll form a cloud at the peak, and then no clouds at the trough, and then a cloud again. So you get these layers of clouds. Looks like striations in the clouds. This is an example of what you might see from gravity waves over the Flatirons here. So these are lenticular clouds that you've probably all seen, particularly on days when we have Chinook winds, and that's exactly what's happening. The Chinook winds are causing the gravity waves to have this kind of condensation here. In fact, the Chinook winds are very warm, right? It's because they've been compressed as they've come down the mountain. Okay, so now back to this image that I was talking about earlier, where we have these striations, the circular patterns here. It turns out that these are caused by waves that were generated in the troposphere. And it was actually fortuitous, really, that we were able to find this out. But on this particular date, 13th of July, 2007, an instrument called the AIRS instrument, which is on a NASA Aqua satellite, saw an area here where it's pretty hard to tell from this image here, but they were able to attribute this to an area of really, really strong convection. Okay? The same instrument is able to look not only at clouds in the troposphere, but also can look up to about the middle stratosphere, 35 to 40 kilometers. And at the same time that they saw this big area of convection here, they saw this ring pattern in the stratosphere. Well, it just so happens that about an hour later, AIM went over the same place in the atmosphere, and this is when we saw these rings, in our data, which are just blown up over here. So we attribute this then to actually the propagation of gravity waves from the troposphere all the way up into the mesosphere. Okay, but one point to keep in mind about gravity waves, and this is going to lead into some of the rest of what we're finding, is that gravity waves only propagate up to the mesosphere if their phase speed, meaning how fast basically is the crust, are the crusts of the waves moving, if that exceeds the zonal wind speed, meaning the wind that goes between east and west. Lynn hates it when I do this because I'm talking in an average sense, but that's okay. So if the phase speed exceeds the zonal wind speed, or if it's in the opposite direction of the zonal wind, then the waves can propagate up. Okay. So this picture shows that happening. You have your wind here. This is the zonal wind. So when it's on this side of the middle line, it's going in an eastward direction. When it's on this side of the line, it's going in a westward direction. These wavy arrows are indicating the gravity waves that are coming up from the troposphere. Okay, as I said, the waves are only going to be able to make it up into the mesosphere if their speed is faster than the zonal wind, or if it's in the opposite direction. So in this case, your zonal wind is going westward. Mostly, you get eastward waves propagating up into the mesosphere. Okay, who cares? Well, the reason you might care about this is when they get to the mesosphere, well, their amplitude is growing and growing and growing, and eventually they break, just like waves in the ocean will break. When they break, they're carrying eastward momentum. So they deposit that momentum into the area where they broke. So if they break in the mesosphere, they cause what we call an eastward drag on the mesosphere. So if, for instance, the mesospheric winds were going in the westward direction, and then these waves break, they're going to slow that wind down and maybe even reverse it. If they're going in the eastward direction already, they're going to speed it up. Okay, so actually, go back to this. So this is actually a picture for the summertime. So we get eastward waves coming up into the mesosphere. They break, cause an eastward drag. That means that you're going to start having an eastward wind in the mesosphere. Okay, so you have summer here, winter here, there's the equator. The eastward momentum from the gravity waves induces an eastward flow up in this polar region. But that eastward flow is balanced by the Coriolis effect. If you remember some of your studies about weather, you might remember that the Coriolis effect acts in a direction that is perpendicular and to the right of the velocity flow in the northern hemisphere. So if you imagine that you're this arrow coming along here, this is going to the right. Okay, so you're going to have equatorward flow. All right. What happens if you have air flowing from the pole to the equator in the mesosphere? Right? It flows and flows and flows. You create a vacuum at the pole? No. It flows and flows and flows, but what happens is air ascends at the pole in order to fill it in. Right? So you get this ascent and cooling at the summer polar mesosphere. So this explains why you have such cold air again. This explains this plot, why you're getting ascent here and then transport over to the winter pole. Okay, so gravity waves drive the really cold mesopause region in the summer, which means that, let's say the gravity waves make it all the way through the mesopause region and don't ever break, they break actually, then that means you're going to get a decrease in PMCs. So we know we have a lot of gravity waves, they're driving the real circulation in the summertime, but we have some gravity waves sometimes that actually break higher and don't deposit their momentum there. All right, and what it turns out is that this happens asymmetrically as a function of longitude. So this is work that was done by Amal Chandran, who's now at NCAR. And what we're plotting here is as a function of longitude. This is the number of gravity waves, basically. Don't worry about the numbers, but this is how many gravity waves you have. Gravity wave signatures in the polar mesospheric clouds that are seen by SIPs. So it's basically counting up those patterns of ripples that we have in our data. And it shows that we have a lot at, say, negative 60 degrees longitude and a lot at 120 or so, but not very many at 60. Right? These patterns are caused by gravity waves going through the mesosphere. Right? Okay. At the same time, you'll see that the number of PMCs is opposite to the gravity waves. Well, that seems to be a paradox, right? Because you have a lot of PMCs, not very many gravity waves. But I just told you that gravity waves cause PMCs. They're what makes it so cold. Well, it turns out if you just have a perturbation, though, on the gravity waves, so that they're maybe breaking higher up and not cooling the atmosphere as much, it just results in a little bit of a heating, a little bit of a difference from the normal state. So you would get fewer PMCs when you have a lot of gravity waves going through, which means they're creating a big signal in the SIPS data, and you get warming. And then just the opposite is happening when you have fewer gravity waves, and then you get more PMCs because it's colder. Okay, so with that gravity wave introduction, and actually that was also the first time that people had really seen that gravity waves on a local scale can actually cause the PMCs to go away. We're now going to talk about teleconnections. So this, I think, is probably the most profound result that AIM has actually been able to show from all of our measurements, in that it is showing, well, a teleconnection, the definition is that perturbations in one region of the atmosphere are communicated to remote regions, even to the opposite hemisphere, via interactions between winds and waves. So from these experiments, what we're able to show really is that one very remote region of the atmosphere, in fact, the troposphere in the wintertime is connected to the mesosphere in the summertime in a matter of days. Okay. So this is one of the results that actually shows that. So this is a paper written by Bodil Carlson, who is at Stockholm University right now. She did a postdoc here. And what it's showing is, well, I'm going to show you that it's evidence of the teleconnection from the winter to the summer. But basically what she's plotting is, again, days relative to solstice on the x-axis, and then what I'm calling the PMC frequency anomaly. All this means really is the change in PMC frequency from day to day. What it is it's the frequency, which is the number of clouds that we detect, the number of pixels in which we detect clouds divided by the total number of pixels on that day, which are in the millions. And what we've done is we've subtracted off a long-term average from that, so we just get very small numbers. But in the black, which shows the PMC frequency, you can see that there's a lot of variability. It goes up and down and up and down. What is really remarkable about this, though, is that this other curve, the gray, seems to be going up and down at exactly or pretty much the same rate, the same time. This other curve is the zonal wind, so again, this east-west wind. But this is not an east-west wind that's anywhere near the clouds. This is the east-west wind in the polar winter stratosphere. We're looking, of course, in the polar summer mesosphere when we're looking at the polar mesospheric clouds. Okay, so we wanted to understand that, and it seems like it was too much of a coincidence not to be something mechanistic. And so what we're saying is that, yeah, the northern hemisphere stratosphere, the winds there are somehow affecting the southern hemisphere mesosphere. Okay. You don't need, yeah, a lot of people can be very skeptical of this. And in fact, a lot of people actually have been very skeptical of this. Seems kind of, well, maybe unscientific to propose something that is teleconnecting from one region to another. Hopefully I can convince you that actually it's not magic. It's real, but it is very complicated. All right, so even though it's complicated, I'm going to try and go through it. Okay, so what we're talking about is teleconnection from the Arctic winter to the Antarctic summer. All right, so it all starts with the Arctic winter, and it actually starts in the troposphere, but I'm talking about the stratosphere here. If you look in the Arctic, in the winter stratosphere, you have what's called this polar vortex. It's a big system of winds that are going in an eastward direction. They're basically circumpolar winds, so they're planetary size scale, basically, you know, going around the polar region. Okay, so this represents kind of the edge of the vortex. These are the winds going like this in an eastward direction. You have descending air inside the vortex, but we're not going to worry about that right now. Okay. A very common phenomenon happens a couple times a year, maybe sometimes in the north, is that planetary waves can come up from the troposphere. So this really does start in the troposphere. And I'm not going to talk about planetary waves. That's too much. But planetary waves come up from the troposphere. They're waves. They're perturbations in the atmosphere. They happen to be westward traveling. So they deposit westward momentum, and they cause what's called a sudden stratospheric warming. So you see in this animation, it's just showing temperature as a function of longitude and as a function of latitude. It's the northern hemisphere winter here. It's showing from mid-December to mid-January of this year, actually. And you can see how it starts to turn really red. That's the stratospheric warming. This is over a month-long time period, but in fact, the temperatures can change by about by 40 degrees easily in a day or so. So this is a very common process that occurs in the stratosphere. All right, so what's actually happening, though, is these planetary waves are depositing their westward momentum. Right? You have an eastward zonal wind. What does deposit of westward momentum do? It's going to reverse the direction, right? So during stratospheric warming, you reverse the wind direction. That's in the winter stratosphere, that you're reversing the wind direction. All right. When the winter wind reverses, that means you're going to get different kinds of gravity waves coming through. All right. So this is the typical situation in the winter hemisphere, near the winter polar region. Again, you have your wind, eastward and westward, and starting out, the wind in the winter is actually in the eastward direction in the stratosphere. So I'm talking the stratosphere here, the mesosphere is up here. Right? So you have an eastward directed wind letting through these westward gravity waves. But when you have a strat warming, this changes, right? It reverses direction so that now the stratospheric wind is in the westward direction, and now your gravity waves are in the eastward sense. So you've changed the amount of drag, the direction of the drag that is going on in the mesosphere when those waves broke. All right, so again, what happens? Well, here's our pole map again. So again, in the winter, this is the winter now, eastward momentum from gravity waves induces an eastward flow. Right? We just saw that because the wind had switched, so now you have eastward waves coming in. Well, same thing that happened last time has to happen this time. The Coriolis effect is going to take over, and you get an equatorward flow. Okay. So equatorward flow in the winter has to mean that the meridional circulation is going to slow down. Why is that? Because, as we've seen, this is the circulation pattern. Air is going up in the summer pole, over toward the winter, and then down. But now we're saying we're inducing an equatorward flow, right? So it's slowing down this circulation here. That means you're going to get less descent at the winter pole, and essentially the whole thing looks like it's kind of moving back this way, right? It was down here, now it's moving back that way, right? But in the summer, you still have your gravity waves coming up just like they always used to. And you still have that normal flow in the summer hemisphere that's causing the summer mesosphere to be really cold. You're getting ascending air here, and it's getting pushed over toward the winter hemisphere. But now you have something that's coming back from the winter hemisphere. So you get this area of convergence right here in the middle, and the air has to go somewhere, and it descends. So you get an induced downward flow at the low latitudes. So what happens when we get downward flow? Air is compressed and it warms. So you get warming at these low latitudes here. So you're warming of the tropical air. All right. Well, if the tropics warm, they're going to induce this temperature gradient between the equator and the pole. Well, there already was a temperature gradient in the summer region, right? You already know the summer pole is very cold. Well, this now just makes that temperature difference even larger. So you have warmer temperatures here that are a lot warmer than the pole. All right? Air wants to flow from warm areas to cold areas, therefore it starts going this way, but the Coriolis effect takes over. At this point, you have to think of yourself as traveling to, say, the south, and then turning to the left, because the Coriolis effect works to the left in the southern hemisphere. And it's going to accelerate the summer winds there, because it's eastward. All right, so what actually happened? This is the original plot here for the summertime. You have your wind. It's in the westward direction in the stratosphere. It actually then comes over and actually is in the eastward direction up in the mesosphere. Your gravity waves are breaking somewhere up in the mesosphere here, and they're eastward. But now, with this sudden stratospheric warming that happened in the wintertime, you've been able to accelerate these winds in the summer mesosphere region. That means that some of those gravity waves are not going to make it through anymore. So they're breaking at lower altitudes. So you've reduced the gravity wave supply. That means that you're going to get less ascent at the summer pole. It's the gravity waves that are really driving this. You're reducing the number, you're going to get less ascent. So you're going to get warming. So less ascent means less expansion. Less expansion means it's not as cold. So that means you're going to get fewer PMCs. So you have a sudden stratospheric warming, which is induced by planetary waves coming up from the winter troposphere. That is felt in the summer mesosphere as fewer clouds. Just the opposite actually happens. You can have it being colder than usual in the stratosphere, and that actually would lead to more clouds in the summertime mesosphere. Okay, so again, sudden stratospheric warmings in the winter stratosphere lead to fewer PMCs in the summer mesosphere. Everybody got it? There's going to be a quiz. Okay, but in case you didn't quite get it all, the important point is really that with the teleconnection, winds and waves interact. That is really the fundamental thing that's happening, is that you have an interaction between these winds and waves. It's very complicated, though. So I would say that they interact with Rube Goldberg appeal. I don't know how many of you are familiar with these Rube Goldberg cartoons. This is kind of the classic one where he's got his spoonful of soup, but he's trying to make a self-operating napkin. So he picks up his soup and pulls on a string, which moves this lever, which moves this soup ladle, actually, which used to have a piece of bread in it. That bread was launched upward. The bird then goes for the bread. That takes the weight off that end, and so the seeds now spill into the bucket, et cetera, et cetera. Eventually, it makes this napkin wet. Very, very complicated. Nevertheless, each step follows logically from the last one. Okay. All right, I think I can have time to go through this. This is another example, actually, of teleconnections, and this work is done by Susanna Benza, who's actually sitting back there. She did some of it, not this plot. Okay, this one was done by Bobo Carlson. Okay, what this shows is PMC frequencies from the SIPS instrument for different seasons. The colored seasons are the Southern Hemisphere 07, 08, and 08, 09. They're these two seasons. The heavy black one is Southern Hemisphere 09, 10. The Northern Hemisphere ones are all in these thin lines here. It's been thought, because of the differences in temperatures, that the Northern Hemisphere always has more PMCs than the Southern Hemisphere. Okay, well, that clearly was not the case in some of this. And in particular, this season, 09, 10, started out really early compared to any of the Northern Hemisphere seasons, and particularly compared to the other Southern Hemisphere seasons. So we wanted to understand what that was all about. Why did it start so much earlier? And the answer is that it's teleconnections, but this time it's from the summer stratosphere. So we're in the Southern Hemisphere mesosphere up here. We're now looking at things that are happening in the stratosphere down below. And it turns out that just in the Southern Hemisphere, this does not happen in the Northern Hemisphere, but the winds in the Southern Hemisphere switch from their winterly state to their summerly state in December. There basically are two states to the winds in the stratosphere. There's a winter and there's a summer. Usually in the Northern Hemisphere, it switches around equinox or so. But in the Southern Hemisphere, the winter winds actually persist from March into December. And so when they switch, they can actually have a large effect on the mesosphere because of the change in the gravity wave filtering that ends up giving. So we've actually gone back in time. This is Susanna's work. To look and see how much this actually happens. So what this plot shows is, as a function of time over the years, it shows from the SPUV data, this is this solar backscatter ultraviolet data, which they also see PMCs with no resolution like we do. It shows the day that the season started, so in terms of days from solstice. You can see this in the black. It varies between about negative 30 days from solstice to as late as maybe 8 days from solstice. In the red is when the stratospheric wind below actually reversed its direction, and you can see an extremely good correlation. There's actually a little bit more going on here that I don't have time to describe. But basically what Susanna was able to show is that back in time, you can really determine what the starting day of the season was based on what the winds in the stratosphere were doing. The other point I wanted to make about this is that the timing of this wind reversal affects and is affected by the ozone hole. So it actually turns out that the PMCs are related to the ozone hole in kind of indirect way. Okay, so I want to summarize then the AIM highlights. We have evidence of turbulence, fractal patterns, rings, and many more things from the PMC images. Ice is ubiquitous at mesospheric altitudes. Meteor smoke is almost certainly the nucleation agent for the PMCs. Space exhaust causes PMCs to increase. Gravity waves control PMCs in several ways, both directly and indirectly. PMCs reveal that via complex teleconnections, distant regions of the atmosphere are inextricably linked together. So regions that we have previously studied in isolation, it's clear that we cannot study them in isolation. We really have to take this whole atmosphere approach to things. Okay, so now, I told you we would have a quiz. Most people are just joking about it. I'm not. Okay, so you guys got to come up. I have some help for this quiz. Now, we are actually going to give you some hints, but this is an audience participation quiz, at least if you feel like it.
In summer cold where the air ascends high above the land and seas, the extraction makes its stroke condensed, forming lots of PMCs. It was launched to study how they form, why they change and what they mean. Though our changing climates do that home, we're consistent, so feed me. Oh, Mesospheric, your clouds cry out to me, 'cause they only show when the sun's down low, a wondrous sight to see. 67
much. Yeah. Oh, you were doing the camera, sorry. Questions, if anybody has any questions. Yes.
Those ring structures that you showed earlier in those swaths, you attributed those to convection, is that correct?
Convection propagating up from, well, okay, let me back up. Let me get those up. If you
I guess the
don't mind.
real question is the bright part of the structure, which is the ring itself, is that is obviously where there are the most clouds, and is that where upwelling is occurring?
That would be where upwelling is occurring.
Isn't the structure where you have upwelling on the outside, is there substance in the middle there?
That's exactly what we think is going on.
Oh, okay, and that's kind of the reverse
Of what you might
the
get.
structure you might get in a thunderstorm, right?
Yeah.
We have upwelling in the middle and
Yes,
substance
yes,
in the end.
that's right.
Oh, okay.
That's right. Any other questions? Yes.
What happened in 2004 on the last slide? The slide that you're outing.
Oh, okay. This guy.
Or,
Oh, I see. Two here?
yes.
Let's see. Missing, well, but it's not really a missing peak because they were both low, right? I mean, is that what you mean? Why were they both low? I can't tell you actually why it didn't go in the same order as normal. I mean, sometimes we look at this and we think, oh, well, maybe there's something like there are natural modes in the atmosphere, natural oscillations like the quasi-biennial oscillation and things like that. But we've checked to see if there was any correlation between those, and there's not. So I don't really know what's going on with that right there.
Gravity waves.
Gravity waves, probably.
No, it's magic.
Yes.
So when would the, taking all of these effects together, when would be the best circumstance in Boulder to be able to see Mesospheric?
You'd probably want to look right around the end of June, beginning of July. You want to look to the north, go up to the top of a 14er maybe at sunset. I keep asking my husband to do that because he likes to shoot from the summits of 14ers, but shoot photos this is. He hasn't gotten any photos yet, but of that. Plenty of photos. Anyway, yeah. End of June, beginning of July.
And then, I mean, so it only happens rarely, and would that be related to something in the southern hemisphere that might? I mean, do you predict these? I mean, we predict space.
It could be.
weather.
We actually we do see these teleconnections from both the north to the south and the south to the north, although they are larger in magnitude from the north to the south than the opposite direction. But it might also be something that's happening even lower in the atmosphere. Unclear exactly all of the things that control the temperature up in the mesopause region, but I would not be surprised if it has something to do with the teleconnection, because these teleconnections really seem to be ubiquitous in causing some of the variations. The solar cycle is also going to cause variations. Now, you're actually coming up on some time when it's probably less likely that you're going to have clouds, a lot of clouds, because the solar cycle, when you get more ultraviolet radiation, it dissociates the water vapor, and so you tend to get fewer clouds at the near solar max than you do at solar min. Right now, we're right around solar max. As we decline into the solar min, we'll see more. Well, you should see more clouds. There are actually some interesting effects that are going on right now that we're seeing an increase in clouds that doesn't quite go with the solar cycle, so we're not sure what's happening. Yes.
It looks like you've got roughly a 2 to 3 or maybe 2.5 year period there. Do you know why that is, or what's it associated with, like El Nino oscillations or something
So
like that?
those are the things that we tried to check when we did check that, and we really didn't see a good association with any of those. Susanna, do you have anything else to add on that?
No, I correlate with quasi-biennial QEO,
Yeah.
which looks like that could be QEO, but it's not correlated.
Right, it doesn't correlate well. I know, I mean, this has the right frequency, but it doesn't correlate well. So yeah, I'm not sure. It's a very interesting question that certainly warrants some extra work to try and figure out what's really causing it. Yes.
So you showed early on a plot that was altitude time of where the ice was, and with the mesopause dashed line
Yes.
on it.
Oh, the Sophie.
And they form underneath the mesopause. Why don't they form at the mesopause?
Well, that's when they're the brightest. They actually are at the mesopause as well. Ice is at the mesopause, but as you form at up high, and then they descend as they get bigger and bigger. They're going to descend, and you see them, where it's at a peak where they're larger, and then as they get lower and lower, as they descend farther, then it's getting warmer, and they tend to then dissipate.
So sweet spot.
Yeah. Yes.
The pictures of the space shuttle flew propagating up to the north were quite dramatic, and I was thinking that must imply that the wind speeds in the Mesosphere are hundreds of kilometers an hour? Or?
I should know those wind speeds off the top of my head, and I don't. But it's actually the plume is actually deposited in the lower thermosphere, around 100 to 115 kilometers or so. And so it's actually the thermospheric winds that are going fast. And this is actually fairly controversial, or has been fairly controversial. I think that we've now been able to convince people that this really does happen. But the models don't generally get it right. They have much slower winds in general. Now, there have been some calculations done by Han-Li Liu at NCAR, and he's shown that under special circumstances, you can get the winds moving that fast. But they're up in the lower thermosphere, and I'd have to do the calculations. I don't know. They're very fast.
There are probably very few direct observations of those winds.
That's right. In fact, no direct observations of those winds. So this is actually pretty interesting to be able to follow a plume by putting together measurements from different satellites of the water, showing where it's going, and then we can see the clouds.
There would have been several tons of chlorine and is it aluminum chloride or aluminum perchlorate?
Yeah. So it could be that you not only have the water vapor that's adding to it, but also maybe some extra seeds. And in fact, there have been experiments been done where they've launched rockets with like silver iodide in them, and I don't have this in this talk, unfortunately, but they've taken beautiful photos of the so-called Noctilucent clouds that form. And this isn't necessarily even in the polar region, but they put so many of these seeds up there that you can see these really spectacular looking clouds that have formed. Other questions? All right. Well, thank you very much.